Hello friends, I am Dr. Divya Haridas. Today I am going to discuss a chapter on measurement in science and technology. Measurement is a basic skill which forms an essential part of our day-to-day activities, irrespective of what we do. You should definitely have observed that while cooking food, measured quantities of ingredients are cooked for a measured amount of time. When you go to buy fruits and vegetables, you take them in measured amounts. You can identify which one of your friends runs fastest. This is possible by making them run a known distance, say from one end of a playground to another end, and noting who is the first to reach the destination. Science and technology helps us in making precise measurements for our daily life activities such as stitching, cooking, sports, shopping, traveling, etc. After completing this chapter, you will be able to answer the following questions. The main objectives. What is measurement and why do we need it? How do we measure? How do we quantify a measurement so that it is understood by everyone in the same sense? What is the currently accepted international system of units? We would also learn about commonly used tools for measurement of the physical quantities like length, mass, time, area, and volume. We may define measurement to be counting of the number of times a chosen scale is used. Why do we need to make a measurement? Suppose you go to the market to buy apples and they are priced at say rupees 50 per kilogram. What would you expect the shopkeeper to do? Would you be happy if he or she gives you 4 or 5 small apples which are surely less than a kilogram and asks for the price of 1 kilogram? Similarly, the shopkeeper will also not like to give you more than a kilogram of apples for the price of a kilogram. An accurate measurement is desirable for both buyer and the seller. The absence of a suitable measurement may lead to conflicts between them. For measurement, we require specific scale which is called unit. Now, what is a unit? First, you imagine a situation. Suppose you are blindfolded and handed a bunch of currency notes. On counting them, you find that they are 46 in number. Can you tell how much money is in your hand? For knowing the exact amount of money, you need to know the denominations. That is whether the notes are rupees 10, rupees 50 or rupees 100 or some other denominations. Similarly, if you are told that two trees are 100 away from each other, how would you interpret it? Are the trees 100 centimeter, 100 feet or 100 meter away? These examples suggest that the results of every measurement must be expressed in such a way that it makes a sense and has a unique meaning. For this, we need to know two things. Firstly, what is measuring standard used, say centimeter, meter or foot, as in the above example, and the number of times it is used. The result of measurement of a physical quantity is expressed in terms of a value. The value of a physical quantity consists of two parts, a numerical part and a unit, and is equal to their product. So, if someone asks you the definition or a simple formula for the value of physical quantity, it would be equal to the product of numerical quantity with the unit. So, what is a unit? Unit is a measure, device or a scale in terms of which we make physical measurement. Now, let us discuss what is a characteristic of a unit. A unit should be relevant for the quantity being measured. For example, if you wish to buy vegetables, you will be using kilogram instead of meter or second. Say 1 kilogram of potato and not 1 meter of potato. Second thing, a unit used should be convenient also. For this, let us take the example of measuring distance. If anybody asks you the distance between your school and your home, then you will tell the distance in either meter, kilometer or miles. But if your teacher asks you the atomic radii, then you won't be able to answer in meter or mile as the dimension is very small. So, it would be convenient to answer in Armstrong or in nanometer. In addition to being relevant and convenient, a unit should also be well defined. The unit, say weight of 1 gram, 1 kilogram, 10 kilogram, which we are using in day-to-day life, should have the same value everywhere. It should not be replaced by an approximate weight. Like when you go to a market, you insist of using proper weights, rather stones, which many vendors use to make profit. So, how did our ancestors make measurements? The need for measurements in measuring devices dates back to antiquity. When the humans became civilized, started cultivating and living in communities, they realized that one cannot do everything and they need to be interdependent. This paved the way for trade, and then probably a need of a measure was felt. Various ways of measurements were adopted. Use of body part for the measurements. The recorded history shows ample evidence that the different parts of human body were used as a point of reference while making measurements. Some of these were digit, the width of a single finger; foot, the length of a foot; cubit, the length of the arm; hand span, the distance between the tip of the thumb and the tip of the little finger when the hands are fully stretched out. Similarly, fathom meant the distance between the ends of the hands when the arms are fully stretched out. It is interesting to note that these are still used sometimes. Certain historical units were based on things around us. Like Romans used a unit called pace, which was equal to the stride of their army contingent, and they called the distance travelled by it in 100 paces to be equal to 1 mile. Similarly, the grain was used as a unit of mass in 16th century and was equal to the weight of a wheat grain. Why there is a need for standard units? The units based on parts of human body are arbitrary and inaccurate. The results of measurement vary from person to person because size of the unit is different for different person. In order to overcome the limitations of body part as unit and to bring about uniformity in the measurement system, the need for exact measurement was felt. For this, a standard of measurements has to be developed which is acceptable to everybody. Now let us discuss what is the Indian measurement system. The measurement system in India also evolved a great deal from the ancient times. In ancient periods in India, the length of the shadows of tree or other objects were used to know the approximate time of the day. Long time durations were expressed in terms of the lunar cycles, which even now is the basis of some calendars. Around 5,000 years ago in Mohenjo-daro era, the size of the bricks all over the region was same. Different units of measurements in the period of Chandragupta Maurya. You can actually see in the screen that they uses different types of units for measurements. Like 8 Parmanus was equal to 1 Rajkand, and Rajkand is nothing but a dust particle from the wheel of a chariot. This particular table has been taken from the reference of Kautilya's Arthashastra. Indian measurement system in the medieval period. In the medieval period also, the measurement system was in practice. As described in Ain-e-Akbari by Abul Fazl-e-Ilami, during the periods of Mughal Emperor Akbar, the gaj was used as a unit of measuring length. Each gaj was divided into 24 equal parts and each part was called tasuj. The system was extensively used to measure land pieces for construction of buildings, houses, wells, gardens and roads. The gaj was widely used as a unit of length till the metric system was introduced in 1956. Even today, in many parts of our country, particularly in the rural areas, gaj is being used as a unit of length. Indian measurement system changed during British period. Now let us discuss what was the measurement system during British period. In order to bring about uniformity in the system of measurement, efforts were made during the British period. The British rulers wanted to connect Indian weights and measures to those being used in Great Britain at that time. During this period, the inch, foot and the yard were used to measure length. Grain, ounce, pounds, etc. were used to measure mass. These units and weights were used in India till the time of independence in 1947. The essential units of mass used in India included rati, masha, tola, ser, maun. Rati is a red seed whose mass is approximately 120 milligram. It was widely used by Goldsmith and by the practitioners of traditional medicine system in India. You can see the picture where it shows a relation between various units of mass used during the British period. The picture shows 3 rati seeds where 8 rati seeds is equal to 1 masha. The modern measurement system. After the French Revolution, the French scientists advocated the establishment of national standard for the purpose and the use of decimal arithmetic system. After detailed deliberations, the basic unit of length and mass were defined and their working standards were prepared. The working standard for a meter was prepared by marking 2 lines a meter apart on a platinum iridium bar. Similarly, a platinum iridium cylinder was constructed equal to the mass of 1 cubic decimeter of water as a working standard for mass. The picture shows the national prototype meter bar number 27, which was made in 1889 by the International Bureau of Weights and Measures and given to United States, which served as a standard for defining all units of length in the US from 1893 to 1960. The 2 standards which have been preserved at the International Bureau of Weights and Measures at Sèvres near Paris. The copies of these were prepared and sent to different countries. As regard the time, the concept of hour, minute and second based on the rotation of Earth was retained. An international treaty called Meter Convention was signed in 1875 to follow metric system throughout the world for trade and commerce. The meter was defined as 1/10 millionth of the distance between North Pole to the equator on the meridian running in France and in Spain. In the course of development of units, a number of systems were adopted. 2 systems which were extensively used were the CGS and MKS system. The CGS system was based on centimeter, gram and seconds as the units for length, mass and time. The MKS system used meter, kilogram and second for the same. In 1958, it was realized that the units defined as standard needed to be redefined. Since 1983, meter is defined as the length of the path travelled by the light in vacuum in 1/299,792,458th of a second. The new exercise of redefining the system of units led to the birth of SI system of units, which is currently the system in use. SI system of units. An international system of units called SI system of units was adopted at the 11th General Conference on Weights and Measures in 1960. SI is the abbreviation of the French name Les Systèmes Internationaux de Units. The SI system of units is based on 7 base units corresponding to 7 base physical quantities. These are the physical quantities in terms of which other physical quantities can be measured. The names and symbols of the base quantities and the corresponding SI units are given. You can actually see that meter is the SI unit for length and the symbol given for this is given by a small m. Similarly, kilogram is the SI unit for mass, which is abbreviated as kg. Second is the SI unit for time, which is given by a symbol small s. The SI unit for electric current is ampere and is being given by capital A. The SI unit for thermodynamic temperature is given by Kelvin and it is symbolized as capital K. Mole is the SI unit for the quantity amount of substance. Candela is the SI unit for luminous intensity and is abbreviated as CD. Let us discuss what are derived units. The base of fundamental SI units like length, mass, time, etc. are independent of each other. The SI units for all other physical quantities such as area, density, velocity can be derived in terms of the base SI units and are called derived units. In order to find the derived unit for a physical quantity, we have to find out the relationship between the physical quantity and the base physical quantities. Then substitute the units of the base physical quantities to find the desired derived units. Let us take an example. Let us derive the SI unit for the area of a surface. In order to derive the unit, we need to find out the relation between area and the base physical quantities. As you know that area of a surface is the product of its length and breadth. So, the first step we write area as area equal to the product of length and breadth. Since breadth is also a kind of length, then to find the derived unit for the area, we substitute the units of the base physical quantities as unit of area equal to meter into meter, that is meter to the power 2, that is m square. Thus, the SI unit of area is m square and is pronounced as squared meter. Similarly, you can check that volume would have SI unit as cubic meter, which is given as m to the power 3. The screen shows some simple examples of the derived SI units of the commonly used physical quantities. You can actually see that meter square, as I already told you, is for area, cubic meter is for the volume, and so on so forth. A number of physical quantities like force, pressure, etc. are used very often, but the SI units are quite complex. The derived SI unit for such physical quantities have been assigned special names. Some of the physical quantities whose SI units have been assigned special names are being shown in the screen. Hertz is the SI unit which has been given to frequency. Newton is the symbol or is the SI unit which is assigned to force. Pascal is the SI unit which is assigned to pressure or stress. Joule is the SI unit which is given for energy or work, and watt is the SI unit for power. Now let us understand SI prefixes. When we make measurements of physical quantities, quite often the quantity being measured is too large as compared to the base unit of the physical quantity. You can see in the screen that the mass of Earth, radius of Sun and the approximate distance between Mumbai and Delhi is given in huge numbers, and it is very difficult to even pronounce those particular numbers. In fact, it is not the huge numbers that we are dealing with. We also face difficulties when we are working with very small numbers. As an example, radius of hydrogen atom is given as 0.00000000005 meters. Similarly, the mass of an electron is given by such a small quantity. It is really very difficult to express either a very huge quantity or a very small quantity easily in a normal day-to-day language. You can see from the examples that when the physical quantity is being measured is either too large or too small as compared to the standard unit, then the value of the physical quantity is quite inconvenient to express. The numbers given above can be simplified by using what is called scientific notation of numbers. In this notation system, we represent numbers as powers of 10. In this notation system, we can rewrite those examples. Mass of the Earth can now be written as 5.97 into 10 to the power 24 kilogram. Radius of Sun can now be written as 6.96 into 10 to the power 8 meters. The approximate distance between Bombay and Delhi is given as 1.4 into 10 to the power 6 meters. Similarly, very small quantity can also be expressed in the powers of 10, like radius of a hydrogen atom is given as 5 into 10 to the power minus 11 meters. Mass of an electron is given as 9.11 into 10 to the power minus 31 kilogram. In scientific notation, the numbers become relatively easier, but are still not convenient because they carry exponent. In order to simplify the numbers further, the SI system of unit has recommended the use of certain prefixes. In the screen, you can actually see certain prefixes or SI prefixes. You are actually using kilo for 10 to the power 3. You are using giga for 10 to the power 9. You will be using for mega 10 to the power 6. And going back to very small quantity, milli stands for 10 to the power minus 3. Micro stands for 10 to the power minus 6. Nano stands for 10 to the power minus 9. But yes, the list goes from 10 to the power 24 to 10 to the power minus 24. How do we use SI prefixes? In order to use SI prefixes, we have to keep a basic rule in mind. The rule is that the prefix is chosen in such a way that the resulting value of the physical quantity has a value between 0.1 and 1000. Let us illustrate with some examples. Like the radius of sun, which is given as 6.96 into 10 to the power 8 meters. This can also be expressed as 696 into 10 to the power 6 meters. In fact, it can also be expressed as 696 megameters. Alternatively, you can also express the radius of sun as 0.696 into 10 to the power 9 meters, or let's say 0.696 gigameter. Now, let us discuss the rules for representing SI units. In order to represent physical quantities in SI units, a number of grammatical rules have been framed. While writing the values of physical quantities, the number and the units are separated by a space. As shown in the screen, you can actually see that 100 space milligram is correct, but not 100 milligram. No space should be given between the number and degree Celsius, degree, minute and second of plane angle. The symbols of the units are not changed while writing them in plural. Example, 10 milligram is correct, but not 10 milligrams. The symbols of the units are not followed by a full stop except at the end of the sentence. 10 milligram dot of a compound is incorrect. In writing the SI unit obtained as a combination of units, a space is given between the symbols. Thus, M space S represents meter second, while MS stands for millisecond. That is, if the units are written without leaving any space, the first letter may be taken as prefix. For the numbers less than unity, 0 must be inserted to the left of the decimal point. Writing 0.928 is correct, but not 0.928 grams is correct. Symbols of units derived from proper names are represented by using capital letters. When written in full, the unit should not be written in plural. Say 30.5 joule or 30.5 capital J is correct, but 30.5 joules or 30.5 small j is not correct. When using powers with the unit name, the modifier squared or cubed is used after the unit name. Say second square, gram cubed, etc. Definitely, area and volumes are exceptions in such cases. The qualifier for the power comes first, that is square kilometer or cubic centimeter. For representing unit symbols with negative exponent, the use of solidus sign should be avoided. If used, no more than one solidus should be used. Say, the unit for gas constant, joule per Kelvin per mole, may be represented as J/K mole, but not as J/K/mole. Now, let us summarize everything, whatever we have learned in this chapter. Measurement is a basic skill which forms an essential part of our day-to-day activities irrespective of what we do. It is a process of comparison and involves counting of numbers of times a chosen scale is used to make the measurement. Measurement is essential for accurate determination of a physical quantity. It is useful in day-to-day transactions, trade and scientific endeavors. The unit of physical quantity is a standard value in terms of which other quantities of that kind are expressed. To be useful, a unit must be relevant to the quantity being measured, be convenient and also well defined so that it is understood by everybody in an unambiguous way. In the ancient times, parts of human body were used for measurements, but these lead to conflicts and confusions because these were arbitrary, non-uniform and lead to results which are not reproducible. Currently, we follow an international system of units called SI units. This system is based on 7 base units which corresponds to 7 base physical quantities, namely length, mass, time, temperature, amount of substance, light intensity and electric current. The units for all other physical quantities can be derived in terms of the base SI units and are called derived units. Some of the derived units have been given special names. SI prefixes are used in cases where the quantities being measured is too large or too small as compared to the base unit of the physical quantity. The grammar of a SI unit must be followed while writing them. Thank you.